225 million kilometers from the Earth sits a planet with red deserts, an atmosphere too thin to breathe, and temperatures that plunge to minus 60 degrees Celsius on an average day. And yet for over a century, scientists, dreamers and billionaires have asked the same question. Could we turn Mars into a second Earth? It's called terraforming, reshaping an entire planet's atmosphere, temperature and surface to make it livable for humans without a spacesuit. It sounds like science fiction, but is it actual science? Today we are separating the physics from the fantasy, what it would take, how long it would really require, and whether serious researchers think it's even worth attempting. The dream is older than most people realize. In the late 1800s, astronomer Percival Lowell became convinced he saw canals crisscrossing the Martian surface, evidence he believed of an advanced civilization irrigating a dying world. That turned out to be an optical illusion, but the idea of Mars as a place that could be shaped and lived on had already taken hold in the public imagination. The term terraforming itself was coined in 1942 by science fiction writer Jack Williamson. By the 1970s, it had jumped from fiction into real scientific journals, with researchers like Carl Sagan publishing serious papers on planetary engineering. Sagan speculated about seeding Venus's atmosphere with algae and, separately, about melting Mars's polar caps to trigger a runaway warming effect. So this isn't a fringe idea invented by a rocket company's marketing department. It's a 150-year-old thread of scientific curiosity that's only become more detailed and more sobering as our data about Mars has improved. Mars is the obvious candidate for terraforming out of every other body in the solar system. It's the most Earth-like planet we have. A 24-and-a-half-hour day, seasons caused by axial tilt, polar ice caps, and clear geological evidence that rivers, lakes, and possibly even an ocean once existed on its surface billions of years ago. But Earth-like is doing a lot of heavy lifting in that sentence. Mars today is a frozen, irradiated, nearly airless world. Its atmosphere is less than 1% as thick as Earth's, and it's overwhelmingly carbon dioxide, not the nitrogen-oxygen mix we breathe. Gravity is only 38% of Earth's, and Mars lost something Earth still has, a global magnetic field. Billions of years ago, Mars's molten iron core cooled and its magnetic field shut down. Without that magnetic shield, solar wind slowly stripped away most of the planet's atmosphere over hundreds of millions of years. That single event is the root of almost every problem terraforming has to solve. And it's why Mars looks the way it does today, instead of the wetter, warmer world it may once have been. To make Mars genuinely habitable, not just survivable in a dome, but walk outside without a suit livable, you'd need to solve roughly 5 massive engineering problems. First, thicken the atmosphere. You'd need to raise atmospheric pressure enough that liquid water can exist on the surface and humans can eventually survive without pressure suits. That likely means releasing huge amounts of carbon dioxide currently frozen in the polar caps and locked in the soil and rock. Second, warm the planet. Mars averages around minus 60 degrees Celsius. Warming it enough to melt ice and sustain liquid water would require a greenhouse effect. Deliberately engineered, the same physics driving climate change on Earth, but used intentionally here, and on a scale we've never attempted anywhere. Proposed methods range from orbital mirrors, kilometers wide, that focus sunlight onto the polar caps, to automated factories manufacturing potent greenhouse gases like perfluorocarbons directly on the surface, to redirecting ammonia-rich asteroids or comets to deliberately crash into Mars, releasing trapped gases and water on impact. Some proposals even suggest darkening the polar caps with dust or engineered microbes so they absorb more sunlight and melt faster. Third, rebuild the magnetic field or find a workaround. Without one, any atmosphere we build gets slowly stripped away again by solar wind, a process that took hundreds of millions of years the first time, but even a partial repeat over centuries would undo real progress. In 2017, NASA scientists floated a genuinely serious proposal, placing a giant artificial magnetic shield at the Mars-Sun Lagrange point, essentially a magnetic umbrella positioned between the Sun and Mars to deflect solar wind before it ever reaches the planet. Fourth, unlock water. Mars actually has substantial water ice at the poles and in newly discovered underground deposits. So the challenge isn't scarcity, it's getting it to melt and stay liquid under the new atmospheric pressure and temperature rather than sublimating straight from ice into vapor the way it currently does in Mars's thin air. And fifth, build breathable air. Even after all that, you'd still have a carbon dioxide-dominated atmosphere, unsafe to breathe. Generating enough oxygen would likely require billions of genetically engineered, radiation-resistant photosynthetic microbes or algae spread across the surface and working for centuries, converting CO2 into oxygen the same way early cyanobacteria did on Earth roughly 2.5 billion years ago, during what's called the Great Oxidation Event. Here's where the science fiction really runs into hard numbers. Some early optimistic estimates from the 1990s suggested a rough breathable atmosphere could be built in a few centuries. But more recent analysis has been far less encouraging. A 2018 study published in the journal Nature Astronomy, led by researchers using data from NASA's MAVEN spacecraft, calculated the total accessible carbon dioxide on Mars, in the polar caps, in the soil, in mineral deposits, and found it isn't nearly enough to thicken the atmosphere to Earth-like pressure, even if every scrap of it were released at once. That doesn't make terraforming impossible, but it does mean the easy version. Melt the caps, thicken the air, done. Doesn't work using resources already on the planet. You'd likely need to import volatiles from elsewhere in the solar system. Icy asteroids, comets, or the moons of the outer planets, each one redirected across millions of kilometers using propulsion technology that doesn't fully exist yet. Factor in building a breathable oxygen atmosphere through biological processes, which on Earth took life over 2 billion years the first time around. And even with drastically accelerated, genetically engineered organisms, most serious estimates land somewhere between several centuries at the most optimistic end and tens of thousands of years at the more conservative end. To put that in perspective, recorded human civilization is roughly 6,000 years old. A full terraforming project, on the more conservative end of the estimates, could take longer than that entire history has already lasted. Even the fastest proposed timelines stretch across dozens of human generations. This was never going to be something one person or even one century finishes. There's also a deeper question underneath all the engineering. Should we? If Mars has any native microbial life, even dormant, even underground protected from radiation the way some Earth bacteria survive in deep rock formations, deliberately transforming the planet's climate could destroy it before we ever find it. That's part of why current missions are so careful about planetary protection protocols, limiting what unsterilized human hardware is allowed to touch on the Martian surface. There's also a practical budgetary argument. Every dollar and every year spent chasing full planet terraforming is $1 and a year not spent on habitats that could support people now, or on searching for that possible existing life before we risk erasing it. Some scientists argue that treating terraforming as the headline goal distracts from the more immediate, more achievable work of learning to live sustainably on a planet that isn't Earth-shaped at all and may never fully be. And there's a middle path worth mentioning. Even without full terraforming, learning to grow food, generate oxygen, and recycle water in sealed Martian habitats builds almost all of the same underlying technology terraforming would eventually need. In that sense, the two goals aren't really in competition. One is simply a smaller, faster, and far more achievable version of the other. So, can we make another Earth? Based on what we know today, the honest answer is maybe, eventually, but not soon, and not easily. The physics doesn't forbid it. The resources and the timeline make it, for now, a project measured in centuries or millennia, not decades. Something closer to a project handed down between generations than a mission with a single finish line. What's realistic in our lifetime isn't a green and blue Mars. It's small, sealed, human-made pockets of Earth, built on top of a planet we're only just beginning to understand. And every one of those habitats is, in its own way, a rehearsal for the much larger project that might come after. Whether that counts as terraforming or just the first careful step toward it, might be the most interesting question of all. Thank you for watching this video, and for more like this, subscribe to Industrial Origin.